Today we're going to do a problem on traveling waves. So in this do-it-yourself video, I'm going to give you a function that has the form of a traveling wave, and we'll give you opportunities to pause the video during different points to work on the problem yourself, and then when you're ready you can resume the video and I will go through how to solve the problem step by step. So to start off with, the function I'm going to give you is this. It is known as the Lorentzian function, for those of you who are curious. And so we're going to explore what this Lorentzian pulse traveling wave, what properties it has, and which direction it's going to travel in. So just for a moment, I want you to think of the properties that this function has without thinking of it as a wave, just thinking of it as a function. What properties does it have? Is it even or odd? What is the general shape of it? So I'll give you a couple minutes, pause the video, and think, and I'll come back. So the properties that I notice about this wave as I look at it are that, first of all, the function is even about the point x equals vt. So the x minus vt quantity in the denominator is squared. So if you have points to the left or right of x equals vt, they will have, if they're the same distance away, they will have the same value of y. So this is good to know when we do the t equals 0 snapshot of the wave. Another thing that I notice is that as x minus vt gets bigger, so at larger and larger x, for instance, for a given time, the function y gets really, really small. It gets small at about the rate of 1 over x squared. Whereas when x is close to vt, when that argument is very small near 0, then the function y is very close to a, because the denominator is very close to 1. So we get something that looks like a pulse shape. Right off the bat, we know that. It peaks in the middle and it tapers off at the ends. It may do something else in between, and we'll explore that when we work on the table of values in the graph, but I know that in the middle it has a certain value and then it tapers away. So now let's construct a table of values. So my question now for you is, what values of x, if we're going to snapshot this of y of x and t equals 0, what values of x should we plug in to make our lives easier for the table? I'll give you a moment to think about that. So the value little a in the denominator there is a constant. Y does not explicitly depend on a, it only depends on x and t. So that's just a number. So I'm going to put in values of x into the table that are integer values of a. This means that I don't have to worry about what a is. I can just get a number out and don't have to carry factors of a with all my x's. So I'm just going to do x equals 0, a, 2a, and so on. So now I'm going to give you a moment to pause the video and fill in the values of y for each of these values of x that we've just determined. So go ahead and do that now. All right, let's see how you did. So the first value I'm going to plug in is x equals 0 for t equals 0. So what we get is we get 1 plus 0 in the denominator, since 0 over a squared is still 0. And so the y value is just a. So we'll put in a there. Let's plug in x equals a. So we just get x squared is a squared divided by a squared is just 1. So we get 1 plus 1 is 2 in the denominator. So we just get a half a, or a over 2. Let's plug in 2a. So 2a quantity squared is 4a squared, divided by a squared is just 4. So the denominator becomes 1 plus 4 is 5. So we get 1/5 a, or a over 5, for x equals 2a. And then finally for x equals 3a, we get 3a squared is 3a quantity squared rather is 9a squared divided by a squared is just 9. 1 plus 9 is 10, so that value is just a over 10. So now that we have our table of values, we remember that this function is even now about x equals 0 for t equals 0. So now we can plot all the negative values of these as well, so we get more bang for our buck. So I'll give you a moment now to plot those values. You can pause the video and do that, and I'll come back and we'll see how you did. Alright, so before I plot, I'm going to clean up some room so I have room for my plot. And I'm going to put on the x-axis integral values of a, so there's a, 2a, 3a, and I'll put them on the minus axis as well. And I'll put a bar that's at the amplitude a on the vertical axis, and now we're ready to plot. So I'll put at x equals 0, y equals a. At x equals a, I'll put a over 2, so just halfway down. At x equals 2a, I'll put a over 5, so I'll estimate where that is. And then halfway up from there is a over 10, so at 3a, I'll just do half of the value I put for 2a, and then I'll mirror those on the negative part of the axis, and we'll draw the curve in. So there's your Lorentzian. It's a very pulse-like shape, so it's very much what we expected from our quick conceptual analysis of this function. And now we're going to figure out, okay, which way is this wave traveling? So we're going to try and determine this x minus vt, does that mean that the wave is traveling to the left or to the right? So I want you to show that it's traveling either to the left or the right, not just memorize the formula. I want you to show that in this case, what does x minus vt mean? All right, I'll give you a moment to do that, and you can pause the video and work on that. Okay, so at this point, to figure out which way the wave is going, we want to pick a point on the wave that stands out, that we can remember where it is. So I'm going to pick the peak at x equals 0 when t equals 0, so the point at the very top, and we're going to see how it changes when t increases. So the peak happens whenever the denominator is equal to 1. So if the denominator has to be equal to 1, that means that the x minus vt squared term over a squared must equal 0. So we're going to set that equal to 0, and we will solve for x at the peak as when t is non-zero. So all we do is we cancel out the a squared, so we can multiply both sides by a squared, and that gets us just x minus vt quantity squared. That term is 0 when the inside term is 0, so just x minus vt has to be 0. And now we add vt to both sides, and we see that x peak is proportional to, or is equal to, vt. So remember, v is the speed of the wave, so it's always defined as a positive value, and that means that as t increases, the peak x value, the x peak, as I've written it here, becomes more positive, which means it's traveling to the right as time goes on. So as t goes up, x increases, which means it's traveling to the right. And indeed, you could try this again with x plus vt in the denominator instead, and you would get x equals negative vt, and the wave would travel to the left. I hope this problem was helpful, and I'll see you next time. Best of luck in your course.